came from Philadelphia. He deserved accolades because he came on the Persian New Year, and he's from Iran. That's a sacrifice. Saman is his first name. He is from Iran, as I mentioned, and he did his undergraduate at UC Davis in chemistry and biology, and then went to Stanford to get his MD. From Stanford, he went to Brigham, and that's where he was swayed in the direction of cardiac EP in Brigham by Bill Stevenson, no other. And from there, it was a short ride to Hopkins, and from Hopkins, even a shorter ride to Penn, where he is now, and he's clinical EP par excellence. So without further ado.
Thanks so much for the invitation to be here. I really enjoyed the trip so far, and really impressed with everyone working here and all the facilities. It's really a pleasure to be back after 16 years and a lot of changes. Really fun to be here. So I'll show you, these are my sort of slides and disclosures. I'll show you sort of a brief summary of a lot of work I've done since, maybe some of it actually during fellowship, and then the rest after I joined the faculty at Hopkins. And I like the fact that it's a smaller group. I'd love to make it interactive, so feel free to stop me at any time so we can discuss in more detail if anything is of particular interest. So the reason I became interested in this is the people at Hopkins, when I first joined the faculty, Henry Halper and some of the folks working there, were particularly interested in developing hardware and software for MR guidance of procedures. So, get this right. And this is where instead of fluoroscopy, you would use MRI and do an ablation procedure under that. And my interest in understanding anatomy and EP came from that, because I didn't see myself particularly as someone who was talented or quite interested in developing hardware or any particular technology for doing this. I think it's going to be very useful, but I saw myself as someone who could help it once it came, because if we get MR, all of a sudden we have this new way of looking at the procedure. It'll only really be translated and be useful in the EP lab if you have an understanding of what, whatever signals you're looking at on the MR scanner mean in terms of the electrophysiologic targets that we're going after. So I'll go over the mechanisms much quicker than I do usually, because you're the masters of the mechanisms, and show you some of the associations between electrophysiology and image-defined substrates that we've looked at over the last few years. So this I always liked. I don't know if you've looked at Alfred Mayer's works, the folks in your training. Really fun to read these. He's sort of the first person to describe reentry. I like it because he was born right next to Baltimore in Frederick, Maryland, and he actually dropped out of school. He wasn't really interested in school. Briefly studied physics because his dad really wanted him to be a physicist, but really ended up loving natural history and became a marine biologist. And he particularly was interested in jellyfish. And he took rings of jellyfish tissue, and if you look at some of his writings from this collection that he published in 1906, these excerpts are pretty incredible. Stimulating any part of the disc, it goes into rapid rhythmic pulsation, the clockwork, and he describes how introducing cuts into these rings, effectively increasing the path length, changes the properties of the rhythm that you see, and even describes reasons why that wave might block if it returns quicker and hits its refractory tail. So amazing description of reentry from him back in 1906, and even the importance of unidirectional block to develop reentry. And then, of course, Ralph Mines, who was an English electrophysiologist and worked at McGill. He described reentry around an obstacle as a mechanism of arrhythmia. He did this in rings of dog tissue and described the vulnerable period of the ventricle. And unfortunately, was at the age of 29, I think, found in his lab, passed out, and shortly after that died. And a lot of people wonder if it was sort of self-experimentation, because that was something that a lot of people did at that time. But a lot of things that he described, which were very interesting, were what is an adequate size of an anatomic obstacle for forming reentry. He talked about the importance of unidirectional walk, and really went into what it means to have an adequate size for that obstacle. So the physical size is, of course, important, and then the conduction velocity and refractory period, and these are things that you would explain to me a lot better, and these are affected by fibrosis quite a bit. And so it makes sense that when we are trying to understand the circuits in our patients in the lab, we would benefit from understanding the fibrosis. And this is where imaging is quite useful. This is sort of showing the pharmacokinetics of gadolinium contrast. When we inject it, it goes up quickly in the blood pool and then is washed out. A little bit delay for it to enter the normal myocardium and scarred myocardium with different kinetics, and we take advantage of the fact that gadolinium perfuses out of scar tissue much slower to sort of enhance areas of scar. And in EP, we use both first pass images for understanding the anatomy and also a delayed image for understanding the properties of the scar. And we worked in the beginning quite a lot on being able to obtain these images in patients with defibrillators. I won't talk about that part of our research, but this is an example of an image that we can get in someone with a defibrillator. So I think you can see sort of a relative darkness here, which is a defibrillator artifact. You can see the lead here, but we can see this area where the gadolinium is kept in the tissue because of the difference in pharmacodynamics here. And you can see this inferior infarct really nicely.
Well, when you have a defibrillator or another metal object in there, how do you deal with that? Do you do anything different in the imaging, or?
We didn't used to. So this image is actually back from when we didn't have sequences to reduce the artifact. And you can see that in this image, we can see the inferior wall pretty well. But if there was scar here or in the anterior RV, we really wouldn't be able to see that very well because of this signal void, because of the metal artifact. So now there are sequences to minimize some of that artifact. It's really, there are two types of artifact that you get. You get one bright artifact. We can almost completely get rid of that now with what's called a wide band sequence. So that bright artifact we can get rid of. But the dark core artifact, which is the nulling up here, that's pretty tough to get rid of.
Okay, yeah, it was the bright one that we had. We had done an animal study where we implanted a pressure monitor, which the company said was MRI compatible. Indeed, it didn't make the MRI bad or anything like that, but the image was this bright.
That's what they usually need.
Yeah, this bright image, it just completely wiped out the image.
This is the CardioMEMS device or another type of monitor?
Yeah, I can't remember the name of the company, but it was an implantable pressure monitor.
CardioMEMS.
Yeah.
I'm surprised it has a huge artifact.
Well, it did back then. That was 15 years ago.
Yeah, so for the bright artifact, you can use the wideband sequence, and it'll completely get rid of it.
Okay, that's nice.
Pam said she's working on getting that sequence soon, so you'll have it soon. What types of scar can we expect to see? These are pretty well described. In idiopathic cardiomyopathy, you can get a linear mid-wall scar, more often in the basal septum. And it was described as 10 to 35%. I think it's about 30% of patients. And if they have a lamin AC mutation, it's much more common to be able to see this kind of artifact. And of course, in ischemic cardiomyopathy, we see scar in 100% of patients. And these patterns are pretty well characterized. So in idiopathic cardiomyopathy, this is the kind of mid-wall scar that we expect to see. Hypertrophic cardiomyopathy, at least in the beginning, they tend to have these kinds of scar in the septal insertions of the RV. Sarcoidosis can really have any kind of scar, but it tends to have some lateral scar, sometimes endocardial RV-based scar, which I think I showed an example of here. This is the kind of endocardial RV-based scar that we can see with sarcoidosis. And then amyloidosis, we were talking about a little bit yesterday. It has this pattern of global endocardial enhancement that we can see also with cardiac transplantation. And then, of course, ischemic cardiomyopathy, the more usual endocardial LV-based or transmural types of scar. And so I'll start by talking about some of the scar patterns and physiology changes that we see, or electrophysiologic associations we see in non-ischemic cardiomyopathy. This was a study that I did in my fellowship where we took patients with non-ischemic cardiomyopathy that were referred for defibrillator implantation, an EP study, and we obtained an image before doing the defibrillator implant and looked at the correlation of the types of scar they had and the transmurality of the scar with inducibility of VT. And we found that if they had mid-wall scar that was greater than 25% of wall thickness, their odds of inducibility was much higher. And in every situation where we induced VT, so for example here with the septal scar, the morphology of the VT was consistent with an exit site near that. So that was sort of early work that told us in the non-ischemic population there is a clear association with this mid-wall type scar pattern. And since then, a couple of other studies have shown that this pattern of scar is very important. So Kathy Wu took 65 patients with idiopathic dilated cardiomyopathy, did a CMR before ICD implantation, and showed that this pattern of mid-wall scar was associated with heart failure hospitalization, this sort of combined endpoint of ICD, firing, and cardiac death. And another study, I think this one was this was with Dudley Pennell in England. I don't think this was at Oxford. I forget where Dudley Pennell is, but he has a terrific MRI group in London. And he showed in idiopathic dilated cardiomyopathy patients that this pattern of mid-wall scar was present in 35% of them, sort of the same number of patients, the same percentage of patients that we saw it in, and it was associated with all-cause death and hospitalization. So clearly, worse prognosis as well as with sudden death and VT. We wanted to look at, so we can see that at a population-based level, it's associated with VT inducibility, with worse prognosis, with ICD shocks and early death, but at EP study was it associated with the findings that we see at a local level when we sample electrograms inside the heart. And in order to do that, we wanted to really characterize the types of scar we see. And in non-ischemic cardiomyopathy patients, it's really quite a lot of different patterns. So you can have endocardial-based scar. You can see this area of enhancement here. You can have the mid-wall scar that I talked about, the most common type of scar that we see in these patients. You can have epicardial-based, whether it's epicardial in the septum, epicardial with respect to the LV, or epicardial lateral-based, another very common pattern. And then you can have these patchy, what I call patchy, sort of going from the endocardium all the way to the epicardium, but more diffuse with a lot of tissue that looks viable near it. And if you look at the distribution of these, so here's most of the time, most of the tissue in non-ischemic patients actually appears normal on MRI. Interestingly, even though it looks normal, if you look at the voltage in these patients, the voltage is far lower than the standard patient, even when there's absolutely no scar around there, which is very interesting. But if you look at the types of scar distribution, so this is essentially just blowing up this percentage, what you can see is it's pretty rare to have a transmural area of scar in these non-ischemic patients, but you can have really any other type of scar. And the transmurality, the great majority are less than 25%. So in our early study, not associated with VT inducibility. And it's really the smaller fraction are distributed between the different areas of different extent of transmurality. Now, if we take a catheter and touch each point inside the heart and correlate the voltage, the bipolar voltage at each of those points, endocardially, these are all endocardial, to the scar transmurality, you see what you would sort of expect, that if you don't have any scar, you're going to have higher voltage, and as the extent of scarring increases, you're going to have less voltage. But what's difficult, and what we run into as electrophysiologists in the lab, is that depending on where this scar is located, if it's mid-wall, our sensitivity for finding that scar is much lower, right? If it's you can have a patient with mid-wall scar have fairly high voltages. Our typical cutoff for determining where the scar is 1.5 millivolts. So we're going to miss that in a good number of these patients with mid-wall or epicardial scar if we're mapping on the endocardium. And this is also true of unipolar voltage. So some groups have used unipolar voltage to determine, in fact, my current group loves to use unipolar voltage to determine where the scar is. And I think it can be useful. I'll show you some of the cutoffs that can be used to find that. But you can see that the distribution, depending on where within the wall the scar is, it can be difficult to find that region of scar. And it's most sensitive really for the endocardium, not for the deeper scar. What we found from this study is that the variation of voltage is least if you use electrogram duration as your surrogate of scar. So it doesn't really matter. As you saw, there was quite a bit of variation depending on where the scar was with voltage. But with electrogram duration, that variation is minimized. So if you have scar, even if it's on the epicardium on the other side that you're mapping, the electrogram duration is a pretty good surrogate of where that scar might be.
This is only for the QRS?
No, this is for the local electrogram sample.
All of it, from the beginning back to baseline, T wave included?
So we often don't see the T wave on the bipolar.
It's bipolar.
Bipolar signal, yeah. So it's
What about in
basically
unipolar? Have you tried to do unipolar?
So the unipolar voltage we've done, that's this. But we didn't look at
The duration.
unipolar duration. I think it's pretty similar to the bipolar duration. But we haven't done that separately. So you get a sense from that it might be useful to use electrogram duration. And so here's, using this data, what we did was try to figure out what the best threshold would be to essentially come up with the same answer as MRI would. So this is assuming MRI is the gold standard. I think it is, but there could be arguments about that. And trying to see if the voltage will match it. So I mentioned that most of the time in our literature, 1.5 millivolts for local endocardial bipolar voltage is considered less than 1.5 unhealthy, less than 0.5 dense scar. So we found that if we set it at 1.8 for these non-ischemic patients, we have the best area under the curve with a pretty good sensitivity and specificity. Unipolar voltage, what we found in this work was less than 5.6. This is when I was at Hopkins. I would never say that nowadays because this is not what the Penn group found. So the Penn group found that the mean endocardial unipolar voltage was about 5.5. But if they had the best results if they set their threshold at less than 8.27. And I think I know why we came up with very different numbers, right? I said less than 5.6. This was from their data. They said 8.27. And their data is from basically taking the 95%. So saying 95% are normal, less than 5% of the distribution should be scar. And so I went back to my data because I wanted to be able to have a discussion with Dr. Mashinsky, and I know he's coming out here soon too. And this is what I found, that if we use the cutoff that we came up with, which basically optimizes the area under the curve, what we have is a 73% sensitivity for finding scar and an 88% specificity. If you use the cutoff they came up with, it doesn't optimize the area under the curve, but it does optimize sensitivity. And I think it just depends on what your goal is, right? If you want to find every bit of scar, there's no question that that cutoff is more useful. And I have to say, I think that's our goal in the lab. It's to find any possible area of scar. So I think you could use either of these cutoffs. But what I really like, and what I've started to use more and more, is this electrogram duration. The AUC is pretty good, with very good sensitivity and specificity. And I think maybe a combination of both of these could be very useful. But I like electrogram duration, particularly for these mid-wall scars, to sort of understand where the substrate is. These isolated potentials are very interesting to us. And so, of course, these are signifying an area of sick conduction, delayed conduction, where you see a large potential, which is usually far field, and then a tiny potential that's delayed, showing that area of sick, very slow conduction. And as you would expect, you'd see more of these as the transmurality goes up. And if we look at areas that actually are proven by pacing techniques, by entrainment, to be within the circuit of VT. So this is in non-ischemic cardiomyopathy patients. Each of these is an area that was proven to be within a circuit. And we look at which one, how do they correspond to scar transmurality. What we find is that in non-ischemic cardiomyopathy, the areas that had greater than 40 milliseconds, so here's the 40 millisecond line, of stimulus to QRS time. So you pace, it takes that long for it to exit out to the periphery of the circuit. So these are the areas we like to be in. They're in the sickest part, they're slowly conducting. They're proven by entrainment to be within the VT circuit, and generally the most successful sites for ablation. So these are all in areas with either greater than 75% scar transmurality or this pattern of patchy scar going from endocardium to epicardium. So those are sites where if I look at an image and I see this kind of pattern, I tend to go to those and search those more. Is it useless to ablate at these other sites? No, these are also areas that have good entrainment values, but they're exit sites, and it's much harder. They're generally much broader, a much broader isthmus, and it's tougher to get success at those sites. Okay, so now switching gears and looking at the ischemic cardiomyopathy patients. Just to go over a little bit of the history of this, I think that the first study that really looked at the pattern of scar and inducibility sort of for risk stratification was a study from the Brigham. And they looked at 144 patients with coronary disease and LGE, followed for a median of 2.4 years. And they showed that the gray zone, which I think probably most people are familiar with it, this area that surrounds the scar that's not as intense, presumably not as dense a scar area, they found that the size of that gray zone, the yellow area surrounding the scar, was associated with overall mortality. So hazard ratio of 1.4 per 10% increase in the size of the gray zone. And so I think that's where the term came from. And then a study from our group, Kathy Wu, where they took 47 patients with ischemic cardiomyopathy, again referred for ICD implantation, and they measured their dense core and their gray zone area of scar and found that the gray zone size was associated with inducible VT. This is from London again, from Dudley Pennell's group and Sanjay Prasad, looking at 373 patients with sustained VT or non-sustained VT, followed for 2.6 years. And they used the composite endpoints, not enough power, so they have to use a lot of different endpoints, but pretty good endpoints, sustained VT, cardiac death, or appropriate ICD shock. And essentially they just divided it into whether patients had LG or didn't have LG. And you can see a very wide separation of the curves, showing a hazard ratio of 3 for LGE, so better magnitude of effect than using LVEF alone, which I think is very important. And with new studies coming on, not in the setting of ischemic cardiomyopathy, with non-ischemic cardiomyopathy, the Danish study showing basically no effect for putting in defibrillators. I really think paying attention to LGE more than just EF is going to be the way to go in the future, but going to be hard to change that paradigm of using EF. And even in the non-sustained VT subset, a very good hazard ratio for using LGE. So the problem with all these studies, though, with gray zone in particular, is that there's different methods for calculating the gray zone. And it's something that we don't talk about a whole lot. But depending on how you study these images, you'll get very different numbers for gray zone and the core. And that's one thing I liked about the Canal study in that last slide, that they just said LG positive or LG negative. Because depending on what method you use, so these are methods that, different methods that can be used. This is full width half max, where you take the signal intensity of the scar and figure it out based on what that peak signal intensity is, or use standard deviations. All of this comes from the fact that it's not like CT, right? With MRI, you have arbitrary units. The magnitude is totally different from patient to patient, and so you can't just say, I'm going to use this cutoff. You have to use these techniques, and depending on which of these techniques you use, and all of them have good validation studies in animals, but depending on which one you use, you'll get very different extent of scar and gray zone. So here, the 2 to 3 times larger if you use the top technique than the other two. And you get very different estimates of the risk for these patients. So I think it's very difficult to use it. And the other issue is, what is gray zone? It's totally, completely affected by the thickness of your slices that you prescribe. So if you have very thick slices, you're going to volume average areas of scar with areas of healthy tissue, and they're going to look gray. They're going to look a little lower signal intensity. If you take very thin slices, you're going to have less volume averaging, but you're going to have a lower signal to noise ratio because you have a smaller voxel. And so all these techniques are tough to apply, and it becomes very difficult.
I think maybe it's good to comment here that this gray zone came from, it came from the MRI and so on, but the electrophysiology community, the experimental electrophysiology, have been talking about the borders of it.
Yeah.
People equate the two. The way the border zone was defined by the EP, early people who did the models in the dog of 5-day-old those were defined as following. Assumption was that the center deep scar and so on is completely homogeneous, completely non-excitable,
Right.
and there is nothing to record from there, and therefore it's safe. The border zone, in their mind, that was Andy Wheat and Penny Boyden and these people, and the border zone is where all the action was.
Right.
That's where you had some heterogeneity, some viable tissue, some uncoupling of cells at gap junctions, slow conduction, and that's where you could have asymmetries, unidirectional block. And turned out it's not the case.
Right.
You can get fractionated electrogram and discontinuous conduction in the middle of the scar. And
Yeah.
it's
And I think that
viable.
idea has percolated along.
But in their experimental setup for 5-day-old LED occlusion, and then the terminology was always used.
Yeah.
And so later came the MRI, and they equated the gray zone with where the action is.
Exactly. And that sort of, it's still, really, if you go to meetings, they talk about gray zone a lot, and the border zone. And I think in some patients, the border zone on the periphery is very important.
Yeah.
But I think that notion that the center is completely dead is completely wrong, and I'll show some data to support that. So here, this is the last study I'll show of looking at the differences in these different techniques for describing border zone and core. And I'm showing this because we really focused on it a lot in the beginning, trying to find where is the area that we should go after in an EP study, because we were interested initially in this stratification like these studies are, but ultimately I wanted to be able to look at this image and say, I need to put my catheter here at that border zone, and that's where the action is going to be. And so, but if I wanted to do that, which method would I use? There are very different implications for the study depending on which one to use. And basically what this study showed is that it didn't really matter. The total scar burden was predicted, but the core versus gray zone changed significantly between which technique you used, and it didn't really add value for risk stratification. And I think the jury is still out. There's still papers being published discussing border zone versus core and which one is more predictive. But my sense is it's probably really just the gray zone is a surrogate of how much scar core there is, and that's probably more important. And from my standpoint, my interest again is to look at specific electrograms that we touch inside the heart and looking at the characteristics of those signals relative to the local image anatomy. And so this is software that we developed where we take electroanatomic maps. We take the XYZ coordinates from Carton. This is from the days where we had point catheters, so we had to touch all of these points. Now we have much denser maps with multipolar catheters, and we can merge the XYZ coordinates of these points to the image and then compare, do an association study comparing each of these point electrograms to the image characteristics. And with this kind of study, this is really what sent me to get my Ph.D. because I felt like I couldn't handle this kind of data. It was thousands of data points per patient. And this is an example that I've made up. These numbers are totally made up. But I just wanted to show you the importance of analyzing this very important, this appropriately, because it's amazing after you've studied statistics for a while and you review papers, what you see comes for review. And I'm sure everybody who's reviewing papers here has had these moments where you look at a study where you have data that's from many, many different patients. Here's just from 2 different patients. So, and if you just pull these and try and get a sense of whatever's on the y-axis with the x-axis, and these are pooled data from 2 patients, and you do a pooled study, you'll get a slope like this, saying there's this relationship between A and B. And then if you account for the clustering, so negative slope here, really strong, looks like a linear association. Then you account for the clustering, and one is patient 1, one is patient 2. You can see that that would totally, completely lead you to the wrong data, right? And this, I think, happens with our medical papers, unfortunately, all the time, because people just pull things together and they don't take into account the fact that, for example, in a patient with healthy tissues, the voltage is going to be just higher than patients with unhealthy tissues, even where there is no scar. And this kind of thing can really bias the outcomes that we have. But for this study, we really wanted to do that. So we used the method of clustering the data by patient. And so this is, I think this was about 20-some patients with ischemic cardiomyopathy where we had 500 plus points from each patient, and each of these points was registered to their image. So at each of those points, we could correlate the electrogram, unipolar voltage, bipolar voltage, electrogram duration, and the number of deflections to the local architecture of the tissue. So something that we don't take into account often is the wall thickness. So we look at scar thickness. We say if the voltage is low, there's scar there. If the voltage is high, there's no scar there. But something that at least I didn't really think about before doing this study is, what about the rest of the wall there? So the wall thickness is really where the voltage comes from. So you could have a good bit of scar in a very hypertrophied septum, and it'll look like normal tissue based on voltage, because the voltage is really coming from the healthy tissue. And so it's all relative to how much viable tissue there is. There's a strong association with everything, including with the number of deflections and with the electrogram duration. And I didn't think it should affect deflections, but it does. If you have healthy tissue separating from the scar, even deflections won't be that good a surrogate. And all of this is also affected by, so wall thickness is important, scar thickness is important, the intramural scar location is important, and then antiarrhythmic drug use. So the electrogram duration, which is something that I had put a lot of stock into, and I still do, we still have to be careful about their antiarrhythmic drugs. So people that are on amiodarone and sotalol will have much longer electrogram duration. So this is a lot of the patients that come for EP studies, and it's hard to get all the amiodarone certainly washed out of the system before we do our mapping. So that can be very tough. But we wanted to see if we could basically non-invasively predict what the voltage map looks like from the image. So this is not ECGI. This is just taking an MRI and trying to see if we can predict where the voltage, what the voltage and electrogram durations and reflections are going to look like. And we could do a fairly good job of this, doing that. But I think the ultimate thing and the reason why I didn't pursue this is you can just import the scar and go where the scar is. But it is interesting that we can predict using these variables pretty accurately where the highest number of deflections, where the prolonged electrogram duration is going to be based on the image itself. But I think this is really what was interesting from the work that we did. So we looked at all the points in these roughly 30 ischemic cardiomyopathy patients where we had entrainment that suggested we were within the VT circuit. So all the points where we had short post-pacing interval after entraining the VT with good concealed entrainment like here. So this is basically a maneuver where we pace in an area where we think we're involved in the VT. We show that we can accelerate the VT. So we clearly have captured the myocardium and we've accelerated the VT. The morphology of the VT during pacing, you can see during this last captured beat, the morphology is identical to the VT morphology in our 12 leads. And when we stop pacing, there's a short return beat cycle length, which suggests we're right within that circuit. So if we look at these characteristics, we see that the exit sites are sort of at what you would call the border zones in areas where you have essentially more than 25% scar, but not necessarily fully transmural. Very few sites that are fully transmural. So 25 to 75% scar in those sites, exit sites. And how do we define that? That's where the stimulus to QRS interval is less than 30% of the VT cycle length. So the time it takes from the stimulus to exit to the surface is less than 30% of the R to R interval during the VT. So these sites were in areas with lower transmurality of scar. And the sites where we really love, the central pathway sites where it's a very thin isthmus of tissue, it's very sick, it conducts slowly, it's a perfect entrainment for the VT. These sites were all in what we would call fully transmural scar when reading an image, right? It's 75% or more. A lot of them on the 100% line. And this is what Dr. Rudy brought up, that the thinking used to be it's all border zone, and the center is not active. So these are all scar core. These are completely transmural infarcts. And yet there is a perfect site with a long stimulus to QRS interval matching that VT. So it's going right through the core of the scar. And if you go back and look at the surgical literature from when they were doing endocardial resections within big infarcts, the interesting stuff and the times where the surgery worked was where they would take the entire core out. And so it's compatible with this kind of data. So in fact, if you take all the areas within an infarct that have greater than 75% scar transmurality and just ablate it all, you would have 100% sensitivity for getting all these scar cores. 65% specificity, but you're ablating that tissue. And that's why door procedure works beautifully for VT, because they're taking out that whole area. And I think a lot of us have changed to that kind of ablation strategy, where we go and completely ablate the core of the scar with fairly good results at this point. So here's an example where I've taken a patient's image and basically segmented the scar. So here's the scar segmented out in gray. And this isn't the border zone or anything. This is just 100% transmural scar. Here's the patient's ICD lead. I just to segment that out just because it helps with registration, so that I can go touch the tip of the ICD lead and register the image that way. The blue is the healthy LV. And then if I register that and do an electroanatomic map, here's the scar in red, matches fairly well with this. And you can see the distribution of isolated potentials marked here in blue dots is right through the core of the scar and even in this patch of scar here. And that's in fact at this point where we had a really good site with nice entrainment, very long stimulus to QRS. So that pace impulse is matched to that QRS. So long exit. And when we look at the return interval, it's very short, exactly on to the VT cycle length, which is a good sign. And then we start burning here, and you can see that immediately within a few beats, the cycle length prolongs and then the VT stops. So again, an example of the dense core being where this VT depended upon. So sort of switching now to another topic within ischemic cardiomyopathy is something I've gotten more and more interested in recently, and this really came about by, we were talking about Stefan Zimmerman, one of my radiology colleagues at Hopkins, who trained at Penn before he went to Hopkins. We were having a research meeting, and he said, what about fat deposition in ischemic cardiomyopathy? And I had never really thought about fat deposition. I think cardiologists in general don't really know that there's fat deposition in ischemic infarcts. I think of fat deposition in ARVC. I didn't really think of fat deposition in ischemic infarcts. And it's amazing, actually, how many patients with chronic ischemic cardiomyopathy have fat deposition. So in our study, we looked at 40 patients with ischemic cardiomyopathy, 20 of them with prior VT, and 100% of them had fat deposition. 20 without any VT before, and 80% had fat deposition. Not a huge difference, but the volume of fat deposition was also higher in patients with VT. And it's fairly common. Radiologists know this because on CT, if you have a certain density, the Hounsfield units below zero, basically, and you can correct me if I'm wrong, but it's nothing else it can be, it's fat. And they have a ton of fat deposition in these tissues if you put a mask on to show those areas with that density. And you can see it on pathology as well. These large areas of fatty replacement within chronic infarcts. And if we brought the fat only, so forget the scar, we just bring the fat deposition into the myocardium. These areas that we're after with isolated potentials, slow conduction, perfect characteristics tend to correspond to the fat deposition. And it makes sense because isolated potentials, we're talking about an area that is really well insulated and it's very slow conducting. And fat is a fantastic insulator. So I've become more and more interested in this, and I don't think we really appreciate the role of fat in the replacement process in chronic infarcts. And
So are you only seeing fat in chronic infarcts? Do you see it in any other cardiomyopathies?
I've only started to look at it in ischemic cardiomyopathy now. I can't say that I've done a ton of CT in non-ischemic cardiomyopathy. In RVC, obviously, it's well known that it's there.
How about in the atria? Do you see it in the atria?
You see a lot of, you might, and I say you might because it's a little tough. The atria are so thin, and you can have so much epicardial fat.
Right, there's a lot of
that it's really hard to say where does that end. I think you need really high resolution time to be able to say better, but I find it hard in the atrium, and it's the same problem with the RV, with ARVC. Is it the epicardium or is it really within the RV myocardium? Resolution becomes more of an issue than with the LV. With the LV, with chronic ischemic cardiomyopathy, it's very clear. It's in the myocardium. But I think in the right atrium, it's a little bit in the atrium, it's a little bit tougher. I have done a study. I actually had a slide on it that I was going to show a little later, but I took it out, looking at the effect of fat on voltage, and it's clear that epicardial fat is associated with lower voltage on mapping in the atrium.
When you record endocardially?
Recorded endocardially.
Huh.
Yeah, epicardially it would be very biased, right? Because if you're over the fat, you don't know if it's
Right.
low voltage. But endocardially, the bipolar voltage is lower in regions where there's a lot of epicardial atrial fat.
So why would that be?
So there could be different reasons. I mean, there's basic studies showing that there are different cytokines released, so there could be actual fibrosis effects. The fat pads, as surgeons know better than us, have the ganglionated plexi,
Right.
so maybe it's an effect based on that. But it's clear that the bipolar voltage is lower in areas where there's a lot of epicardial fat. So this is again LV fat in this chronic ischemic cardiomyopathy. You can see that isolated potentials essentially restricted to areas that had fat deposition either right there at that point or just adjacent to it. And we don't know that it's there if we just get an MRI. So here's a patient where we had both an MR and a CT, and you can see the contrast enhanced CT here, where this is clearly fat deposition, highlighted here with this mask just showing in purple the areas of fat. These are clearly epicardial, but this is clearly myocardial fat deposition. And it's the same area. The whole thing lights up on LG-MR. So a lot of what we see on the gadolinium enhanced MR is a mix of fat and fibrosis. And there are sequences for MR to do fat water separation and sort of figure out what's fat, what's scar, but we don't usually do them. And the resolution, I think, at least in our hands, hasn't been as good. So really the way to do it is to get a CT to find the fat, and if you're interested in separating it, get an MR, and I think the subtraction image would give you what's fibrosis, what's fat deposition. And then I'll end the ventricular work with this. This is just a direction I'm going in, trying to use CT because I want to see the fat, seeing if on CT, on perfusion CT, we can figure out where the scar is. And there's a decent correlation. The slopes aren't all identical, but decent correlation between bipolar voltage and the attenuation that's during perfusion CT to see where the areas of scar tend to be. So this is data that we're analyzing now. We have data from 125 patients that had PT ablation and had CTs baseline and after ablation, and it's basically the work I'm doing with my current grant, looking at both the changes that we see after ablation, what changes are needed to have a successful ablation, and then also cardiac remodeling. We've looked at it before with echo, showing that we don't negatively affect cardiac remodeling after ablation, but that's just with echocardiography, which is not really great at looking at the entire remodeling process. And I think it would be important to look at CT, use CT to look at it.
Can I ask a technical question about how you're recording your bipolar?
Yeah.
Bipolar is going to be dependent upon the direction the wavefront hit.
Yes.
That's it. So are you pacing?
In general, what I try to do is I try to do it during RV pacing. Some patients, they're really dependent on their BIV. And so I would say a small fraction of patients, if they do better hemodynamically, I keep them BIV paced.
So my question I'm getting to is, if you pace from a different place, would these relationships hold up?
They should. It won't be perfect, but in general, yes, the relationships hold up. You're absolutely right that with bipolar electrograms, the direction of activation matters, and also the direction of your bipole matters a lot.
Right. Yeah.
So our data for the CT study is mostly with multipolar catheters, where the bipoles are generally in the same, and they're much smaller electrodes, so they're better quality data. But those limitations stand.
So do you guys have like target tip electrodes that would be omnidirectional?
Omnipoles?
Not yet.
Not yet.
Okay. I mean that's.
It's in development.
Yeah. I mean that's what.
That has its limitations too.
Right, but at least it's less sensitive to the direction.
Why not do unipolar?
Yeah, that's what I was
Better
getting.
way.
Well, so that we have, all of this is with unipolar also. The associations are all very similar.
Okay.
And the ones I showed you before were both bipolar and unipolar. So, but yeah, in general, I like RV pacing, and the reason for that is most of our scar is in the left ventricle. And I find that if I'm recording during RV pacing, I'm more likely to see the isolated potentials because I'm pacing from farther away, and it's more likely to bring out those delayed potentials. Whereas if it's BIV pacing, I think it just squishes all the signals together.
The problem is if your bipolar is perpendicular to the wavefront, you measure nothing. Depends on the angle.
It depends on the angle of contact.
Right.
It doesn't depend for sure on the angle of
And
contact.
that's a strong dependence.
Yeah. Yeah.
So bipolar is a good thing to do.
Yeah. And unipolar. Yeah. No, we look at unipolar. The problem with unipolar is the signals are just much smaller. It's really hard to see an isolated potential on unipolar mapping. I think the catheter matters a lot, and the direction matters a lot, and that's why when we can, we use these high-density pentaray catheters where they have a lot more holes on them. The problem is they tend to be a lot more arrhythmogenic. In the cardiac surgery setting, you can put it on the epicardium, and I imagine it's not as arrhythmogenic. But our catheters, the pentaray...
You got to push so hard, yeah.
Our pentaray, yeah, it's just wherever you put it, if it's healthy tissue, it's causing PVCs, and it's really hard to interpret that at that point. So it's a limitation for sure. It's a good point. So now I want to skip over to the atrial side. I'll skip this stuff because this is bringing to Newcastle. So functional reentry, obviously a very different mechanism, probably less dependent on SCAR, but I think my point of showing some of Alyssa's work before and showing this is it does matter, and I think we talked a little bit about that the diffuse fibrosis reduces conduction velocity, and it probably can help to perpetuate functional reentry, maybe even provide an anchor to stabilize it, although we have found no evidence for that in humans. Here's a patient without any AF, and then you have architectural disarray, interstitial fibrosis in AF. So there's already evidence that fibrosis does occur more in AF patients. And I don't know, maybe this data is from WashU, is it? I wasn't sure.
I don't know, that's
So patients, this is data from mitral valve patients showing that interstitial fibrosis is significantly higher in patients with AF. The transverse diameter of the remaining cells is larger, so they tend to hypertrophy, and the capillary density is lower in AF patients. And amazingly, these estimates are actually pretty close to what we find with MRI. I'll show you in a second, depending on what threshold we use. And it's helped us decide on the thresholds. This is something that I found interesting. The degree of LAA fibrosis, left atrial appendage fibrosis, is actually less than right atrial appendage fibrosis. And it's, I found this surprising. Initially, we started looking at the right atrium also, and I haven't published any of that data because I felt like we were seeing too much scar in the right atrium. And in fact, even in patients that had absolutely no history of AFib, healthy volunteers, we saw areas of enhancement in the right atrium. And I've actually now started to think maybe I should go back and look at that data, and maybe it wasn't junk because I was talking to Vadim, that I found out today was from this institution, and he was telling me that he has found the same thing, that he's doing a lot of MRI work and has found that a lot of, basically there's fibrosis in the area of the sinus node, and there is and the embryology is different, so there is more expected fibrosis in the right atrium. So maybe it wasn't all an artifact, but we found a lot of fibrosis in the lateral wall and in the right atrial appendage, even in, well, I shouldn't say fibrosis, delayed enhancement. And I don't know what it comes from, but there is a lot of fibrosis, and this paper also shows in patients with AF, the burden of fibrosis is higher in the right atrium. And that makes you wonder also about our strategy of totally ignoring the right atrium in these patients and doing everything in the left atrium. So this is to show that we can apply the same technique for imaging fibrosis. This is a patient after laser ablation, and I show you this because I think it's the most beautiful picture. The most beautiful pictures after ablation we see in laser patients, because I think when we're doing radiofrequency ablation with a catheter, even though our electroanatomic system tells us that we're making this beautiful line, I don't think it's really as beautiful a line as it is. So when I get an MR image after RF ablation, it's often the whole atrium looks thicker and lights up. But with laser, and here's the reconstruction of the same patient, you see this beautiful ring. I mean, some areas that have been spared, but it's a really nice modality, and it really shows up beautifully on these MR images because it's it's a balloon, it's very stable, and it's a focal ablation. And so the MR pictures of the laser patients are really what convinced me that we're seeing something real and dependable, because they're in perfect agreement with where the laser was applied.
Have you done any of this with the cryo balloon? Because that
Yes.
probably makes a nice big lesion for you to.
That's what I expected, but I don't know why. I don't see much. So with the cryo balloon, I think the mechanism of injury must be different. Maybe it takes longer. These are 24-hour post images. So at 24 hours, we certainly don't see this. Maybe it's a little bit more osteal, and the thinner the tissue gets, the harder it is to see it. So no, with cryo, I don't see much.
Yeah.
But with laser, it really lights up beautifully. So we started out doing this, about 4 or 5 years ago. Mostly I had been focused on the ventricle before that, and when Nasir started looking at this, Nasir Marish in our field, we wanted to do some work, and using the standard deviation techniques, we've really been focused on sort of trying to figure out the best way to analyze the images so it's reproducible every time. And it's tough, because depending on where you pick your normal region of interest, what you say is normal, and how many standard deviations above that to scar, you get very different values. And if you use the standard technique that they've published, what we get is so this is now correlating to voltage maps, whether there is LGE and whether that agrees with a voltage less than 0.5. We get a positive predictive value of 0.8, negative predictive value of 0.7, and these are the sensitivity and specificity, I think, are not so good specificity. And I don't think this is enough to guide therapy. And the other thing is, if these were a number of patients with redo procedures. So we had done an ablation before, and we were going in there, and initially we thought we would be able to predict where there was a gap. And if there was a gap on MRI, there was definitely an electrical map. But if there was no gap on MRI, it did not mean there was no electrical gap. So like in this patient, the lasso catheter, which shows us where the gap is, showed us there was a gap right here. And the late gadolinium enhancement is this purple area here in this patient. So it was right in the middle of that dense area. So I think the resolution is an issue for finding gaps. So we can definitely not do that. I don't think it's ready to find gaps. We worked on trying to find a different way, and I talked about the fact that the intensity is an arbitrary unit. So we worked on normalizing the intensity, basically dividing the intensity of each point by the blood pool, and then coming up with thresholds. So as we went with more and more patients, we looked at the thresholds, and we've come up with, I think, pretty stable numbers. So this is over patients, and now we're at over 300. But essentially the confidence interval keeps narrowing, and for less than 0.5 millivolts, we came up with an image intensity ratio of 0.96, I think was the number, and 1.6 for less than 0.1. And which one is more appropriate? I think 0.1 is more appropriate. We don't have in EP a good threshold, right? Some people use 0.1, some people use 0.2. I don't know what you use epicardially, but there's no good threshold. What is scar, what is not? But I think if you compare it to histology, I showed you those numbers of 7% of the left atrium being scar by pathology. That corresponds more to the less than 0.1. So I tend to use less than 0.1 more and more for my studies. And so we wanted to correlate this to function to see if it was real, what we were seeing. The areas of scar, are they really scar, and do they translate to function in the atrium? And of course you showed us some nice speckle tracking data. So this is doing the same sort of thing. So here we took 90 patients with with AF, and we looked at their extent of enhancement, so mild enhancement being with that threshold that corresponds to 0.5 millivolts, dense enhancement with 0.1, and you can see the studies by Karate that I showed by pathology said 7%, so our estimate came to pretty close to 7% if we used 0.1 millivolts, and too high if we used 0.5, and that's why I think 0.1 is more appropriate. And then we divided these by paroxysmal and persistent, and you can see that the numbers make general sense. There's more enhancement in the patients with persistent AF, and of course the volume in persistent AF is higher. And then we had a number of healthy volunteers where we developed these normal values in brackets from. And then this is where the speckled tracking came in. So the same software, well, I don't know if it's the same exact software, but the same techniques that you use for echo can easily be applied to CT or MR. And the nice thing is nowadays we don't have to do the tissue, we don't have to do the tagging. So you can use a cine image and use this kind of software. This was, we do it for this original study, we only did it in 2 cuts. So a horizontal long axis cut and a vertical long axis cut. And examine the association of the function with what we saw as scar to make sure that it actually made sense. If there's more scar, there should be poorer function. And this is true. So although I will say that parts of it surprised me. So I always thought the more scar you would have, the more effect it should have on the active atrial function. These are all patients with sinus rhythm, so they were, even if they were persistent AF, our practice, at least at that point, was that we would put them on an antiarrhythmic agent and cardiovert them about a month before the ablation procedure, because we felt that there was some data at that point that if you make the patient stay in sinus rhythm before the procedure, you have better odds of affecting cardiac remodeling and having a beneficial effect from ablation. In practice, I think it also helped stratify patients. If they couldn't be cardioverted, we probably shouldn't be ablating them. But it also helped my study because these numbers would be meaningless if they were in AFib. So they were all AFib patients, but the persistent ones had been cardioverted a month before this study. And so here's the interesting thing, the passive EF. So what is the passive EF? The passive EF is the atrial ejection during the conduit phase as opposed to during the pump phase. That's significantly different between persistent and paroxysmal patients. But the active EF is not different. That surprised me. It's really the passive, the conduit phase that's affected by the extent of scar and by the phase of AF the patient is in.
Did you somehow look at the ventricles to see if, because the passive, the conduit and reservoir function are a function of the ventricle?
Yes, absolutely.
And so is it the patients, for instance, that have persistent AF have lower LV ejection fractions?
That's a good question. I have to go back to the paper to look at that, but what I can tell you is that so we looked at T1 mapping in the ventricle to see if there was more diffuse fibrosis in the ventricle in persistent versus paroxysmal, and there was no difference in the diffuse fibrosis in the ventricle. And I want to say the EF was not statistically different, but I have to look back. I don't want to say that. But I think they were similar. In general, it's rare for us to ablate, at least it was rare for my prior affiliation to ablate patients with LV dysfunction, ablate AF in patients with LV dysfunction. Now we ablate a lot of them, but at least when we were doing this, we didn't ablate a lot of patients with LV dysfunction. So I think almost all of them had preserved LV function. And then the strain values are as you would expect. So peak longitudinal strain very different between persistent and paroxysmal patients, much lower in persistent, and the same with different strain rate measures. So a clear gradient between persistent and paroxysmal AF patients, and what was really promising to us that we were measuring something right was that these were all correlated with the extent of fibrosis that we measure. So here's 2 patients that I'll show you as an example. The dotted line is the one with a lot of fibrosis using our image intensity ratio, and the solid bar is one without much fibrosis. And you can see that the volume is the volumes are much higher in the patient with a lot of fibrosis. The peak global strain is lower, and all these strain rate values are also a function of the extent of fibrosis. So clearly the fibrosis is closely associated with atrial transport function. And then we wanted to look at, this is a different study, looking at conduction velocity, whether what we were measuring in terms of gadolinium enhancement affected the conduction velocity. And this is by bipolar mapping. And it's not perfect. I think in front of this audience I have to be very careful how much I try to sell this, but it's with it's a multipolar mapping catheter, and basically we had a script written that took the average conduction velocity of between 1 point and its 5 neighboring points, and correlated that to the extent of enhancement here. By no means perfect, but in all of those patients during pacing from the high right atrium, so uniform direction of activation. And I think the results are at least something that makes sense, that they're clearly associated with the image intensity ratio. So the faster conduction velocities were associated with lower intensity, and interestingly also associated with thickness, which I think also makes sense. The thicker the tissue, the slower the conduction.
So where's that recorded at? You're looking at, you're showing here. Is this endocardial?
Well, this is just a map of showing the conduction velocity encoded in these colors, and then the thickness and the image intensity ratio. It doesn't show any geographical pattern. It's just displaying the conduction velocity as a function.
So you're not concerned of conduction velocity over 2 being a little high for physiology?
Those points were very rare.
Okay. Yeah, I kind of, when I see conduction velocities that high, I get very suspicious that they're not, there's something else going on.
Fishy. Yeah. No, those were very, I should probably cut off, because there's some outliers and those are probably junk data. But the bulk of the data is really here. And then if you look at these, in patients with paroxysmal and persistent AF, not a huge difference, but it's statistically significant that the conduction velocities are lower, median value is lower than paroxysmal AF, and the distribution shape is a little bit different. So there's a clear difference between those types of patients, and it's affected by the extent of scar. Now, why, if you have the scar and it's more prevalent in persistent patients, why should ablating improve things? Why would we create more scar? And in this study, we wanted to see what the characteristics were of ablation-induced scar as opposed to pre-existing scar. And again, these are, I should probably change the scale on these to show the differences a little bit better. But what you can see is that the intensity is clearly higher in ablation-induced scar, so more dense pattern of fibrosis probably. And the wall thickness is I think, fairly dramatically different. The whole thickness is not, it's atrial tissue, so it's very thin. This is millimeters. But clearly thinner post-ablation compared to the novo scar in these patients. So I think the idea is that with ablation, we create essentially a more homogeneous, dense scar and reduce that heterogeneous scar that probably increases the likelihood for more sustained functional reentry. And then what we wanted to look at was sort of reproducing some of the work from Utah, looking at whether the extent of fibrosis really does affect the hazard for recurrence of AF after ablation. So our database was 165 patients at this point, over half paroxysmal with a single PBI procedure. And what we found was that this line really crossed at 35%. Now this is using the 0.5 millivolt cutoff, not the 0.1 millivolt cutoff. So if they have more than 35% of their atrium with less than 0.5 millivolt voltage, or it's equivalent in MRI, what we found was a much higher odds of recurrence. And if we divide the groups based on paroxysmal and persistent, and whether they have more or less than 35%, what we found was that paroxysmal versus persistent really didn't make a difference at all. It was really just a function of how much scar. So, and I think that is what I've found in practice. You go sometimes into an atrium and you're voltage mapping, and the whole thing is red. It's what people have called a strawberry atrium. I don't know why it's strawberry, because the green part is missing. But if it's all red, it just seems like nothing is going to come off that ablation, and they always go back into some sort of tachyarrhythmia, AFib, or tachycardia, and keep coming back for more ablations. Whereas even persistent AF patients, when you go in there and the voltage is healthy, they tend to have pretty good results. So I think it's real, but the images are tough to obtain, and we have. What I didn't mention is that a lot of these patients are handpicked to be the good images, so we do exclude patients with bad images, and that's a real problem, because with AF patients, there's going to be arrhythmia, and sometimes the images aren't perfect, and so I don't think it's prime time. I wouldn't exclude any patient just based on this, but I think certainly what you can say is that we need a different strategy for these patients with a lot of scar, and I don't know what that strategy is. There's now data from Australia that if a lot of these patients have sleep apnea, hypertension, obesity, and they have data that shows that if you control these comorbidities, the extent of fibrosis changes, which really surprised me. I wouldn't have expected the extent of fibrosis to change. But if that's really true, and that can be reproduced, then ablating all the fibrosis makes no sense. And that's sort of the new craze, is to go, say, if the pulmonary veins are isolated, let's ablate everything that looks low voltage. And that seems totally wrong if the extent of fibrosis can be changed. So I don't know what the answer is for that. But I'll conclude here. So I think in the setting of non-ischemic and ischemic cardiomyopathy, it's clear that for risk stratification, there's a lot of utility for scar imaging and understanding the substrate. And I think hopefully in the future, ICD implantation will be better guided by using techniques based on imaging and or ECGI, something that's a better surrogate of what's going on, what's responsible for their arrhythmia. I think EF is a horrible measure, and at least in the setting of non-ischemic cardiomyopathy, it definitely doesn't seem to identify patients that benefit a lot. And I think it's clear that the action for us is in the dense regions with enhancement. So I find it very useful to take images from cardiac MR and merge them into the procedure and essentially focus all my attention on those dense scar regions. For AF, I think there's a lot more work to be done, but I think there is a way to understand the pattern of scar, and it does seem to correlate with function, which is a pretty good surrogate of where the scar should be. And it's pretty clear that AF type isn't that important. I think AF persistence is less important than their atrial function. And I think that's also very important for the other challenge that we're dealing with, which is anticoagulation after ablation. You have a patient that you ablated that have no AF, and they really want to come off their blood thinner. I think probably the AF is just a sign that their atrium is sick, and they shouldn't be taken off the blood thinner even if they don't have AF, because the extent of scar is still there, their function is still horrible, and I think there's probably a lot of room for speckle tracking, for functional imaging, to see what their flow should be like and whether they should be anticoagulated or not. But a lot of fun work to be done still. So thanks again so much for inviting me, and really enjoyed the day.
Thank you. Thank you very much for a wonderful, that was really extensive. I don't know when your taxi is supposed to be here, is it not?
5:40.
5:40.
It's
Been
5:50.
waiting.
And it's gonna.
So I think we'll have to do with questions, because otherwise you might miss your flight. You're welcome to stay another night.
I think Frank would be mad if I miss clinic tomorrow. But
Thank you. Any something short burning?
Just one comment I wanted to make is you really hit the nail on the head about this persistent versus paroxysmal. I think we really need to start being able to define the actual burden,
Yeah.
because there are some people with paroxysmal who have it all the time basically, and then there's people with persistent who are out of it for months at a time.
Yeah.
And so without having that, it's not surprising that always comes up to be a little, the data, it never really separates very well.
That's the problem with definitions, right?
Yeah.
Right.
So if you guys need his contact information, I do have it.